Eigenvalues are -1 and 2 in this case. Now, by the Cayley-Hamilton theorem, the matrix A will satisfy its characteristic equation. So this means in this characteristic equation, you replace lambda by A. So you get A square minus A minus 2I is equal to 0. Okay, so this is because of the Cayley-Hamilton theorem. Fine. Now, from this equation, which we have obtained by the application of Cayley-Hamilton theorem, we can say that A square is equal to A plus 2I. Now, we multiply this equation multiply by A, both sides. So on the left hand side, you have A raised to 3. And on the right hand side, you have A square plus 2 into IA. Identity matrix times the matrix A gives you A. So you get 2A. So that means we have, when we multiply this equation by A, we get this equation A raised to 3 is equal to A square plus 2A. Now, we have this A square on the right hand side. And from the previous relationship, A square is A plus 2I. So we can replace this A square by A plus 2I. Fine. And another 2A is there. So that we do not change. And then you add them together. So you have 3A plus 2I. Fine. So what we get here is that A square, A raised to 3 is equal to 3A plus 2I. Now you multiply both the sides again by A. So this A raised to 3 will become A raised to 4. And on the right hand side, you have A 3A square plus 2A. Now we have A square again on the right hand side. So we can use this value of A square. And then we can write this as 3 into A square is A plus 2I, and plus 2I is already there. So this gives you 3A plus 5I. Okay, so this means that A raised to 4 is equal to 3A plus 5I. Uh, uh, oh, no. So sorry. So we had 2A here because after multiplication, this identity is 2 into I into A is 2A. Okay, so you get 5A plus 6I. So some small mistake in the calculation. So that means A raised to 4 is 5A plus 6I. So you have A raised to 4 is equal to 5A plus 6I. Fine. Now you can repeat this process again to get A raised to 5. So we have A raised to 4 is equal to 5A plus 6I. Now you multiply both the sides again by A. So on the left hand side, you have A raised to 5. On the right hand side, you have 5a square plus 6a. And then again, you use a square is equal to a plus 2i. Substitute this here. So you have 5a plus 2i plus 6a. And this gives you 5 plus 6 is 11a and 10i. Okay. Right. So you have a raised to 5 also in terms of a and I. And then you can multiply this equation by a both the sides. So you get 6a square after simplification. You get a raised to 6. You get a raised to 6 is equal to 21a plus 22i. Okay, and you can proceed in the same way. So if you are given a matrix A and you are asked to find the value of a raised to 6, you can obtain this value using the Cayley-Hamilton theorem. Okay, so first application of Cayley-Hamilton theorem we have seen, where we have calculated the inverse of the matrix. Now in the second application, we are calculating the positive integer power of the matrix A. Okay, using the Cayley-Hamilton theorem. Fine. So now if I ask you to calculate the value of a raised to 6, so a raised to 6 is 21a plus 22i. You substitute the value of a, substitute the value of a here and the identity matrix, add them together. So a raised to 6 will come out to be this matrix. In general, you can write the matrix a raised to m. Okay. So from the above relationship, we can see that for this example, every power of A is a linear combination of the matrix A and the identity matrix. Therefore, we can say that the mth power of A is equal to C naught I plus C1A, where C naught I and C1A are unknown constants that we want to determine. Okay, so if m is equal to 2, if m is equal to 2, then you get this. And in that case, C naught is 1 and C1 is 2. If m is equal to 3, you get a raised to 3 as 3a plus 2i. And in that case, C naught is I think C naught is 2 here, and C1 is 1. So here C naught is 2 and C1 is 3. When a raised to 4, you have 5a plus 6i, and in that case, C naught is 6 and C1 is 5, and so on. When a raised to 6, you have 21a plus 22i. So this means C1 is 21 and C naught is 22, like that. So in general, AM can be written as the linear combination of the matrix A and the identity matrix. Okay, now we want to calculate these constants C naught and C1. Fine. So how do we calculate these constants? We use a fact that we learned in our previous lecture. We then this fact is that this fact is following. If lambda is an eigenvalue of A, then lambda raised to m is an eigenvalue of A raised to m. This we have seen in our past lecture. So we are going to use this fact, right? So this means that a lambda raised to m is an eigenvalue of am. This means that A raised to m x is equal to lambda raised to mx. Fine. So in this relationship that we have assumed, we can multiply in this relationship, multiply both sides by the vector x. So on the left hand side, you get A raised to mx, and on the right hand side, you get C0I plus C1A times the vector x, okay, which can be written as A raised to mx, left hand side remain the same, and you can bring this vector x inside, so you get C0. So from here, the right hand side will be C0, I into x is x, and the second term is C1 ax, but ax is lambda x, because lambda is an eigenvalue of the matrix A, right? So you get C0 x plus C1 lambda x. You can take this x outside, so you get C0 plus C1 lambda x, this relationship. Okay, on the left hand side of this equation, so we have reached up to this point. So let me erase and then. So that means we have reached up to this point now. Now the left hand side is lambda raised to x, because if lambda is an eigenvalue of A, then lambda raised to m is an eigenvalue of am, which means amx is equal to lambda raised to mx. So A raised to mx can be replaced by lambda raised to mx. Okay, so you get lambda raised to mx, and right hand side is C0 plus C1 lambda x. Okay, and since x is non-zero, so you can write this. You can take this x common. You bring the left hand side to the right hand side to the left hand side, and take x common. Okay, and remember that x is an eigenvector corresponding to the eigenvalue lambda of the matrix A. Therefore, x cannot be 0, right, from the definition of the eigenvector. So if x is not 0, the only possibility for this quantity to be 0 is that this should be 0, right? So this is 0, means lambda raised to m is equal to C0 plus C1 lambda, right? So using these facts, we are able to now come to this relationship. Lambda raised to m is equal to C0 plus C1 lambda. Now we have two unknowns, C0 and C1. If we are able to find two equations for these two unknowns, if you are able to find these two unknowns, if you are able to find two equations corresponding to these two unknowns, then we can solve these equations. So, this is the equation which is which corresponds to this is the equation which corresponds to the eigenvalue. And eigenvalue we have already calculated. You see that we have the eigenvalue here. Lambda is equal to -1 and 2. So that means if I put lambda is equal to -1, then this equation will be satisfied. And if I put lambda is equal to 2, then also this equation is satisfied, because this holds for any eigenvalue, lambda of A. Okay, so this is what we are going to do here. We substitute the value of lambda in this equation. So when lambda is equal to -1, left hand side is -1 raised to m, right hand side is C0 plus C1 into -1. Okay, so we get one equation, C0 minus C1 is equal to -1 raised to m. When I put lambda is equal to 2, I get the second equation. The left hand side is 2 raised to m, and the right hand side is C0 plus C1, 2. So that means we have these two equations now. Okay, corresponding to these two eigenvalues. Fine. So you have first equation is C0 minus C1 is equal to -1 raised to m, and the second equation is C0 plus 2C1 is equal to 2 raised to m. You have two unknowns, C0 and C1, so you can solve these two equations. When you find the solution will come out to be this. C1 will be 1/3 inside the bracket 2 raised to m minus of -1 raised to m, and C1 will be this. When you do this solution, 1/3 2 raised to m plus -1 raised to m, right? Fine. So that means we can substitute the value of these constants C0 and C1 in the relationship that we have obtained, is that A0 A raised to m is equal to C0 plus I, C0 into I plus C1 into A. So substitute the value of C0 and C1. So you have this is C0. You substitute this value here, and this is C1. You substitute this value here, right? And then you substitute the value of A. Value of A is this one. Substitute here, and the identity matrix. Identity matrix in this case is 1 0 0 1. Okay, and then do this simple addition of two matrices. You will get A raised to m as this, and this will hold for any m equal to 1, 2, 3, and so on. Okay, and you can indeed verify that this calculation is correct if you take m is equal to 2. If you take m is you get this relationship here, am is equal to this matrix. So if you take m is equal to 2, then you can see, or maybe if you take m is equal to 6, then you can see that A raised to 6 will indeed be this quantity. Is this okay? So using the Cayley-Hamilton theorem, one can calculate this power of integer power of A, positive integer power of A. So it reduces the calculation a lot. The example that we have seen here for this is for the matrix of 2 by 2 order. So for 2 by 2 order, calculating A raised to 6 is not a complicated task. But if the size of the matrix is big, then it may be helpful to use the Cayley-Hamilton theorem to find a raised to 6. Okay, so we have demonstrated this with the help of 2 by 2 matrix. Is this fine? Any question here?
Sir, here C naught equals to 1 by 3 times 2 raised to power m minus 1 raised to power m plus minus 1 raised to power m. Sir, when we take LCM, it will become plus 2 times minus 1 raised to power m in right side.
So you mean to say that this expression is wrong?
Yes, sir, C naught. Yes, sir.
So 2 is missing.
Yes, sir.
Okay, so calculation you can check. If you find some, this is mainly the typing error. So if you find any typing error here,
Yes, sir. Rest is fine. Rest just the matrix, the A raised to power m matrix is fine.
yeah, I also see that this the little x should be the bold x, because vector and matrices are denoted by bold letters.
Yes, sir.
Okay, and also here a raised to m should be bold.
Yes, sir.
Okay.
So
Any?
to find a general equation of a raised to the power.
You are not audible. Can you unmute yourself and then speak?
Hello, sir.
Yes.
So I'm asking that
I cannot hear you.
hello.
Yes, go on.
Sir, I was asking that to find out the general equation of a raised to the power m, do we need to first identify the trend? Like here we got to know that a here's a linear combination of a and I, but this might not be true for every matrix.
That you can get from the Cayley-Hamilton theorem itself. Okay,
So how?
if you have like you have a square matrix, then Cayley-Hamilton theorem says that it will satisfy its characteristic equation. So something like this. So for this is the general one. So you want to express a raised to m in terms of the linear combination of the identity matrix, matrix A square, A square, and A raised to n. So again there is a typing mistake. So this should be m minus 1. You don't want to go to the higher order, otherwise it will not work. Okay, so this method is basically to simplify your calculation for the power. And in many cases it will simplify. It does not mean that in every case it will simplify. For example, if you have a diagonal matrix and you want to find a raised to m, then immediately you can calculate for diagonal matrix. You don't need to go through this calculation. This calculation will become more complicated will be more time taking for the if you are dealing with a diagonal matrix. Forget about diagonal matrix. If you are dealing with a zero matrix and you are asked to find a raised to m, where m is any positive integer, then you can immediately say that this is a zero matrix without doing any calculation. And if you start doing this calculation, it will take more time. Okay, so in many cases, this will simplify your calculation for a raised to m. That is the purpose. It does not mean that whenever you are asked to find a raised to m, you apply this. If the question specifically says that you have to apply Cayley-Hamilton theorem to find a raised to m, then you have to show the process. Okay. Otherwise, you can use the usual matrix multiplication also, provided it takes less time. Okay. Is this fine?
Yes, sir.
Yeah. So now you have a little homework. You can do this. So I keep this for you to read. You check these calculations for these constants. You check this relationship will hold for you find the eigenvalues, and then through the eigenvalues you identify this relationship, solve these for substitute the value of the eigenvalues in this equation and solve this for the constants, these constants. Okay. So I leave this for you to read. This is just the extension of the previous example for the 3x3 matrix. So nothing complicated at all. Okay, so that completes the Cayley-Hamilton theorem. Now we move to the next topic in this section. This is diagonalization of a matrix. So for this, we need the notion of similar matrix. So we say that. So we have the first definition. We say that two square matrices A and B are similar if there exists an invertible matrix. Denote this invertible matrix by P such that A is equal to B, P, B, P inverse. Okay. So two square matrices A and B are said to be similar if there exists an invertible matrix P such that A is equal to P, B, P inverse. In other words, you can say that AP is equal to PB, or in other words, you can also say that P inverse AP is equal to B. Okay. And this similarity thing will be very useful that we will see later. So now the next is we need a special notation to write down our proofs, and this special notation is that if you have any general matrix A and another matrix B, let us say that the columns of B, the first column of B is this one. So we denote this first column by x1. So this is the first column of B. And the second column of B is this one. So we denote this by x2. Okay. Now if we multiply A and B using the usual matrix multiplication, this multiplication will come out to be this, right? And from here we can see that the first row, the first column of this product can be written as the matrix A times the first column of B. Okay, so this is matrix A and the first column of B. So when you do this product, you basically multiply the first row by this one, and then the second row by this one. So you get these two elements in the column vector. And similarly, the second column of the product can be written as A into x2. Okay, so this notation we are going to use in our subsequent calculation. So in general, so this was for the matrix of order 2 by 2. If we have two matrices A and B of order n by n, the same thing can be extended, where we can write the product of the matrix AB as the first column of the product can be written as A into x1. The second column of the product is A into x2. And third, the nth column of the product is A into xn, where x1, x2, xn are columns of the matrix B. Is this fine? So this is the notation we will use frequently in our proofs. Okay, so keep this notation in mind. Once again, the product AB is this matrix, where AX1 is the first column of the product, AX2 is the second column of the product, AXN is the nth column of the product, X1, X2, Xn are the first, second, and nth column of the matrix B. So this should be X2, another typing mistake. Okay, this should be X2. Fine. Now, let us come to the statement of this theorem. It says that the eigenvalues of two similar matrices are same. Eigenvalues of two similar matrices are same. The definition of similar matrices we have just seen. Okay, so two matrices are similar if there exists an invertible matrix P such that AP is equal to PB. Okay, or A is equal to PB P inverse, or P inverse A, P is equal to B. Okay, so this theorem says that if you have two matrices which are similar, then their eigenvalues are same. Fine. So to prove this theorem, we will show that the characteristic equation of these two matrices are same. So if the characteristic equations are same, the eigenvalues will be same. So let us go through the proof. So we say that A and B are two similar matrices. This means that there will be a non-singular matrix P such that A is equal to P, B, P inverse. Now we start with the characteristic polynomial of the matrix A, which is the determinant of A minus lambda I. We can substitute the value of A here. So this will be equal to determinant of PA, PB, P inverse. So you have this P, replace this. So when you substitute the value of A, this becomes PB, P inverse. And the identity matrix that you have here, you can write this identity matrix as PI, inverse. PI is P. When P is multiplied by P inverse, you get I. So this is basically I. So replace this I by PI, P inverse. Okay, so you have this PI, P inverse. Fine. So we have reached up to this expression. Now you can take P and P inverse outside. So you get a determinant of P into determinant of B minus lambda I into determinant of P inverse. Okay. And this will be equal to determinant of B minus lambda I, because determinant of P inverse is equal to 1 over determinant of P. Okay. So this terms and this term cancels out. So you are left with the determinant of B minus lambda I. Okay, so that means we are able to prove that the characteristic polynomial of A, which was determinant of A minus lambda I is same as the characteristic polynomial of the matrix B, where B is similar to A. Okay, but now if you equate this to 0, you get the eigenvalue of B. If you equate this to 0, you get the eigenvalue of A. So we can say that since the characteristic equations for the matrices A and B are same, therefore the eigenvalues are also same. Okay. So the utility of this result is that if the matrix A is complicated and you are able to find a matrix B with many zero entries such that A and B are similar, then instead of finding the eigenvalue of A, you can find the eigenvalue of B, and with the help of the eigenvalue of B, you can also say that the eigenvalue of A is same. Okay, so this is the utility of this theorem. So instead of dealing with a complicated matrix A, instead of finding the eigenvalues of a complicated matrix A, we find the eigenvalue of a less complicated matrix B if A and B are similar. Okay, right? And this will become more clear if we go to this diagonalization of the matrix here. So that is the next definition. This says that a square matrix is diagonalizable if there exists a non-singular matrix P such that P inverse AP is equal to D, where D is a diagonal matrix. So in simple word, if A is similar to a diagonal matrix, then A is said to be diagonalizable. And A is similar to diagonal matrix means that there exists an invertible matrix P such that P inverse AP is equal to D. Okay. So from the previous theorem, you can easily see that instead of calculating the eigenvalue of the matrix A, if A is diagonalizable, then we can calculate the eigenvalue of the diagonal matrix, because all the entries in the diagonal matrix except the diagonal elements are 0. So finding the eigenvalues for the diagonal matrix is easier. In fact, the diagonal elements will be the diagonal elements of the diagonal matrix will be the eigenvalue. Okay, so no need to calculate the eigenvalues of A. You just calculate the eigenvalue of the diagonal matrix, and then you get the eigenvalue of A if A is diagonalizable. Okay, so this is that is why I said that this theorem is very useful. Instead of dealing with the matrix A, you deal with a simple matrix B, which is similar to A. Fine. Now we have so this is just to explain the notation. I can go directly to this next theorem. So this next theorem says that basically whatever written here is a special case of the proof here. So this is just to motivate the students that I have written this on the slide. So now we can go to the next theorem, which says that an n cross n matrix is diagonalizable if and only if A has linearly independent eigenvectors. So this theorem has two parts. One part is if A is diagonalizable, then we have to show that A has n linearly independent eigenvectors. The second part is that if A has n linearly independent diagonal vectors, then A is diagonalizable. Okay, so basically this is if and only if condition. So if somebody asks you to define diagonalizable matrix A, then you can use this as also as the definition, because this is if and only if condition. So you can say that if I ask you to define diagonalizable matrix, so you can say that A is a diagonalizable matrix if and only if A has n linearly independent eigenvectors. You can treat this as a definition. Okay, so we prove these two parts one by one. The first part. So assume that A is diagonalizable. By the definition of diagonalizable, we can say that there exists an invertible matrix P such that A is equal to P D P inverse, or AP is equal to PD, where D is a diagonal matrix. Okay, let us say that this is the diagonal matrix we have with the diagonal elements D11, D22, Dnn, and matrix P, using the notation that we have just introduced, is written as P1, P2, Pn, where P1, P2, Pn are the first, second, dot, 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 nth column of the matrix P. Fine. Now we start with using this notation. We consider this relationship. So from this relationship, we get left hand side is A into P. A into P, we have said that we have just introduced the notation here, where we say that the product can be written in this form. Okay, so here we have matrix P instead of matrix P, and the columns of the matrix P are P1, P2, Pn. So that means we can replace this x1 by P1, x2 by P2, and xn by Pn. So you have AP1, AP2, APN. So AP can be written in this form: AP1, AP2, APN. And right hand side is the product of P with the diagonal matrix D. So P is this one. The first column of P, the columns of P are P1, P2, P. And when you multiply this by the diagonal matrix, you have you will get D1, P1, D11, P1, D22, P2, and so on, Dn and Pn. Okay. So from the relationship and the notation that we are using, we will get from this relationship AP is equal to PD, and then in the notation that we are using, we get this relationship. Okay, now you compare these two sides of this equation one by element wise. So first element is AP1. This will be equal to D11 P1. So you get the relationship AP1 is equal to D11 P1. The second one element is AP2 is equal to D22 and D22 P2. So you get this relationship. And lastly, you have APN is equal to DNN PN. So you get APN is equal to DNN PN. Okay, so you get this relationship. Fine. So you have this relationship. This N relationship you have. Okay. Now P is invertible, right? So that means none of the columns of P will be 0. If any one column of P is 0, then the determinant of P will be 0 and P will not be invertible. So since P is invertible, so every column of P should be non-zero. So we can say that P1 is not equal to 0, P2 is not equal to 0, Pn is not equal to 0. Fine. So this means that since P1 is not equal to 0, if you consider this first relationship A P1 is equal to D11 P1, so you are able to find a non-zero vector P1 such that A P1 is equal to D11 P1. So we can say that D11 is the eigenvalue of the matrix A. Similarly, the second relationship is AP2 is equal to D22 P2 and P2 is not 0. So from the second equation, we can say that D22 is an eigenvalue of A. And the last one is APN is equal to DNN PN. From this, we can say that, and Pn is not equal to 0. So we can say that DNN is an eigenvalue of the matrix A. Okay. So from this these equations, we can conclude that the eigenvalues of matrix A are D11, D22, so on to DNN. And this is another important result. Although this is part of the proof, but it is an important result. If A is diagonalizable, then the diagonal elements of the matrix D are the eigenvalues of A. Okay. So if A is diagonalizable, you do not calculate the eigenvalue of A. You calculate the eigenvalue of the diagonal matrix, and the eigenvalue of the diagonal matrix are the diagonal elements. Okay. And the corresponding eigenvectors are P1, P2, Pn. P1, P2, Pn are corresponding eigenvectors. Right. Now, we also see that P is non-invertible. That means rank of P is n, if which is the order of the matrix. The order of the square matrix P is n. P is n cross n matrix. Okay. And P is non-invertible. P is invertible. That means P is non-singular. This means the rank of P is equal to n, which is the order of the matrix. Okay. So if rank is n, then we can say from the definition of the rank that there are n independent columns of P. So this means that these n columns are linearly independent. These n columns P1, P2, Pn are linearly independent. Fine. So we get our final result, which is that the eigenvectors P1, P2, so on to Pn are linearly independent. Fine. So the first part is complete. Now we move to the second part. In the second part, we will assume that A has n linearly independent eigenvectors, and then we will show that A is diagonalizable. That means we have to show that there is a matrix P, non-singular matrix P, invertible matrix P, such that AP is equal to PD. This is what we want to show. So we start with this second part. So we assume that eigenvectors let us say P1, P2, Pn are eigenvectors of A, and these eigenvectors are linearly independent. Now these are eigenvectors, so we'll have corresponding eigenvalues. So corresponding to eigenvector P1, let us say lambda 1 is the eigenvalue. Corresponding to eigenvector P2, lambda 2 is the eigenvalue. And corresponding to eigenvector Pn, lambda n is the eigenvalue. Okay. So this means we will get A P1 is equal to lambda 1 P P1. A P2 is equal to lambda 2 P2. And A Pn is equal to lambda n Pn. Fine. P1, P2 are eigenvectors. Lambda 1, lambda P1, P2, Pn are eigenvectors of A. And lambda 1, lambda 2 are eigenvalues of A. Corresponding eigenvalues. So you get this relationship here. Now we create the matrix P with the help of the eigenvalues, eigenvectors of A. So P is, we define P as a P1, P2, Pn, where P1, P2, Pn are eigenvectors of A. These are linearly independent eigenvectors that we have assumed at the beginning. So that means P is non-singular, determinant of P is non-zero. Because you cannot write any column of P in terms of the linear combination of the remaining n-1 columns. So whatever row transformation or whatever column transformation you do, you will always get the rank of P as n. And if rank of P is n, which is the order of the matrix, then the matrix P is invertible. Okay. So if we define P is in this way, then this relationship that we have obtained can be written in this form. Immediately you can see. Okay. So that means we are able to find, and where D is this matrix. The matrix D is constructed with the help of the eigenvalues. The eigenvalues are lambda 1, lambda 2, lambda n. You put the eigenvalues in the diagonal of the matrix, and the remaining entries of the matrix are 0. Okay, so from the relationship that we have obtained, from this relationship, we get this relationship. Okay, so that means we are able to find an invertible matrix P such that AP is equal to PD, where D is the diagonal matrix whose diagonal elements are eigenvalues of A, and P is an invertible matrix whose columns are the eigenvectors of A. Fine. So from here we can say that another typing mistake, A is diagonalizable. Okay, so this is not invertible, this is diagonalizable. Fine. Any question?
Sir, no question till now, but that one doubt was remaining.
Yeah.
About the uniqueness part.
Yeah. So I will revise my slides and so bring more clarity in my slides, and then I'll send it again. Somehow there is some problem in my iPad.
Sir, I tried proving the uniqueness, but I'm stuck in one step.
So you can send. You are in which batch? S3.
S7.
Okay, so you can send your solution to me, and then I can check. on my email.
Okay,
or
sir.
even on my WhatsApp number.
Okay.
Okay, so today I will stop here. But the thing is that since I'm explaining things in more detail and my lectures are going slow, so I need another extra lecture this week. So I guess today is Wednesday, so hopefully you are free from after 4 onwards. So now you are free, I guess. So if you wish, we can take a break, and then we can take a 5-minute or 10 minutes break and then continue. Because I want to finish this topic. I want to start the next section, in fact, in this week, and I have only one lecture.
So there's a club intro from 4:30, I guess.
There is a club intro from 4:30, so we can go up to 4:30 today.
Yes, sir.
If it is fine with everyone.
Yes,
Is it all right?
Yes,
Sir,
sir.
I have a doubt.
Anyone has any objection if we go till 4:30?
So you can take a separate extra class, 1 hour.
Sir,
Separate
when is extra class?
that you have to tell. The CR will have to tell me. I can go till 4:30 today, or we can fix one extra class. Which one is comfortable with you?
Sir, extra class.
We can fix one extra.
Extra class. Okay.
Yes, sir. Extra.
So then the task will have to find a time when everyone of you are free, and I am also free. Then we can take that.
In which week, sir?
This week,
Any day.
either today, tomorrow, or Friday, or Saturday, or Sunday. So